And so I didn't use the word virtual image when I was doing the flat mirror. I was kind of saving it for now, but the flat mirror and this scenario are each virtual. They appear to be coming from there. And it kind of makes sense. If the light ever appears to be coming from behind the mirror, it must be virtual because it never could come from behind the mirror. The light never really could be there. And of course, if it appears to be coming from in front of the mirror, well, then there it really could be coming from there. And most likely is coming from there. And so the images that are in front of the mirror, this one would be real, and this one over here would be real. And so I'll add to that and put real. So we've got 2 real images and 1 virtual for this, what I'll call the fun mirror. And then the flat mirror only gives us the virtual one. Now, this scenario, if I, again, keep drawing, and so let me get my blue marker here. If you remember, I've been doing blue to represent a triangle that has the object and then the image in the mirror. So let me take the object, so here is the object, and the image in the mirror, and let me make 2 blue triangles. In fact, these 2 blue triangles are overlapping. You might miss that there are 2. Do you see 2 blue triangles here? Do you see what I will call the small blue triangle here that has the object? And then the big blue triangle that is the size of the image? And let me put some numbers up here. This is the height of the image, so it's the same as the height of the image right in here. And this is the height of the object. Okay. This distance right here would be what we would call the object distance. That's how far the object is from the mirror. And of course, this over here we would call the image distance. So in this case, the image distance is inside of the mirror, which of course it's a virtual image. It's just like we did for the flat mirror. It's a distance inside, but notice it's always measured from the mirror. And then of course, this right here is the focal length, and so that means this shorter distance right here would be focal length minus object distance. Because if I then draw my first equation here, I would say take the big triangle, so the height of the image is to the height of the object, so this height is to this height, as this length, which is focal length, is to this length, which would be focal length minus object distance. And if you compare that over to here, you'll see that it is not quite the same equation that we've got in the other 2 scenarios. And this denominator has been switched. And you can kind of see that when you think of this as taking maybe I'll start with these, taking these 2 blue triangles and picking this one up and folding it back onto top of the bigger one, you then get this picture. And so there's a slight change in the equation because there's a slight change in the position of how those triangles are laid out. And so like I said, it's too bad that it's not quite the same equation. Because it certainly would make it much easier to memorize. You can just memorize one time and be done. But it doesn't come out that way. And so that's why I like to go through this geometry. And now once I go through the geometry, I think it'll be easy for you. At least I'm hoping. That's why I'm going through the geometry. Now let me try the other set of triangle, the green one. So here's the green one. And if you remember when we drew the green one involved a triangle that had the height of the image, okay, and it also had the height of the object projected into the mirror. And so I hope this isn't getting too messy here, but now I think you begin to see why I think you need a little help and direction running through this geometry compared to just figure it out on your own. But if you look at that green set of triangles, and I'll say the same thing. I hope you see the green small triangle inside of the bigger green triangle. And since they're laying on top of each other, they are similar to each other. So we can do this. We could say the height of the image, so there's the height of the image is to the height of the object. So this is to this, as this whole length. Now this whole length would be focal length plus image distance. See, because this, from here to here is focal length, and from the mirror to the image is image distance. So I'm going to add those two over this, which is then the focal length. And so again, we get a slightly different equation. And so here's where you're going to need to be careful when you do the homework and the test is, okay, what do I have? Because to use this set of equation, which I'll say it again is the same as this set of equation, you can use each of these set of equations. They would be true for the concave mirror if your object is outside of the focal point. But to make it clear, I should put a box around this and say this would be the set of equations you would use if your object distance is less than the focal point. And so these are the two set of equations. And I guess I should also emphasize that this is true only for the concave mirror. You wouldn't use this for the flat mirror, and you're not going to use it for the convex mirror as we begin to discuss. And so really you have two sets of equations, but you have three different results. And so this is why I call this the fun mirror, because look at the three different results. We can get something that is smaller upside down, or something that is bigger and upside down, or something that is bigger and right side up. That's what this mirror does. And it's kind of fun to see this. And so I was showing you the concave mirror, here it is, concave mirror last time. Let me hold it up. Why don't I start with scenario number 3 here. This scenario number 3 says if you took an object that was close to it. So here's my mirror, and I'll kind of give you a side shot. I don't know if you can see it kind of curve inward, but if I was guessing, I would say the center of curvature is about right here. So if I cut that in half, right here would be the focal point. So if I were to put an object closer to that, all right, so I will put an object maybe right about there, this blue marker. And so, Ron, can you see the image in there? Yeah. And does it look right side up? And does it look bigger? Okay. And maybe to give you that effect, maybe I'll even move its distance a little bit. Because notice it is, you know, within this range, it is always bigger. It is always right side up. But how much bigger depends on where it is located. And so that's why I can't just say, hey, what is the size of my image? I got to sit down and do a calculation, because you can see in the math the height of the image would depend partly on where is the location of the image. And that's why these are what I call the fun mirrors, if you change its location. You ever been to a fun house? The fun houses love to use mirrors that are curved because you see some weird things, and this is just one of those things. This would be the case where you would see your image and it would be inside of the mirror. And it would be bigger and it would be right side up. But you might also recall this first scenario that I said if the object was far away from the mirror, you would get an image that is small and upside down. And so I'll take this mirror, and maybe you can look at the cameraman Ron in there. And so Ron, you're gonna be my image. You got the camera there. You can wave at him. But I'm hoping what they can see is you and the camera upside down, smaller. Now they probably can't tell that it's coming from actually right here in front of the mirror. That's a little hard to tell, but as opposed to behind the mirror. But to show you that it's actually in front of the mirror, this is where I think this one comes better into play. This one is curved much more. In fact, it's called a hemisphere because it literally is half of a sphere. And I say that because if I were to put something straight in front of it, straight down, and I'll do that